Okay, hello. So everyone, yeah, I'm just gonna be recording a very nice video about oscillations today, and this is a simple learning objective review, and you can treat it as like the revision before you grind the question. Now, before we start in, I just want to make sure you get everything in order. So what you should be doing is like sit down properly on a table, watch this using your computer, and then you should have with you list of basically your full scat. And if you have an iPad with you, it'd be good if you can also bring up the notes. Now, if you're wondering where you can get the notes, it's simple. You can head over to the website and then go over to the question bank, head over to Teach to Physics. Make sure you select the 2025 syllabus, right? And then subsequently go and find oscillations. Now, once you click view topic notes, this was actually the notes that you have from last year. Okay, and so actually oscillations is a really big topic and it accounts for a very large share of the marks. So I've actually split it up into two different sets of notes. Okay, so you'll need both of this. And on top of that, it will be very good if you are also following along the learning objectives here. And so you can just search up on Google H2 Physics 2025 syllabus and just click on the first link. I visit often. Okay, so yeah, click on this. And then head over to the oscillations part, and then yeah, we'll run through iteratively each of these learning objectives. Okay, so you can pause the video and get everything in order, and then for me, I'll start over on a blank sheet of paper. Now, this is truly a blank sheet of paper, but I will be referring to the learning objectives here. Okay, so once every objective is over, I'll come back and then strike it off. Okay, so we can start on this. So let's just title this as oscillation. Okay. And the very first learning objective is describing simple examples of free oscillation. Okay. So let's figure out first for learning objective A. Then I'll define it this way. A free oscillation is one where there is no external damping force. Okay. So at the same time, there's nothing, right, that is, let me write that up. There is also no force that restricts the frequency to a certain value. So what I mean by this is you basically vibrate at the natural frequency if you're having a free oscillation. Okay? So you must remember there's a natural frequency associated with a free oscillation. And I can give you a couple of examples. So the most basic free oscillation you get is one where there's a spring, something like this, and then you have a block of mass m. Okay, so I think you can already visualize that if I were to displace this by some distance x, then it will experience a net force in this direction. Okay? And so we can think of it this way, the F, right, that it's experiencing is also called the restoring force. Okay. And it's quite similar to circular motion in the sense that there must be some force providing for the restoring force. And we call it the restoring force because it restores the position back to equilibrium. Okay, so if you can visualize, like when I drag this fella here to the right, it will bounce back, right? So it'll just swing back and forth. And it will swing back to the equilibrium position, which is somewhere in the middle, something like this. This is what we call equilibrium position. Now, if you're wondering why it's been called the equilibrium position the whole time, it's because there is no resultant force at the equilibrium position, and therefore it's called equilibrium, right? So there's no net force at that position. Okay, but anywhere else, there is some kind of restoring force to bring it back. Okay, so this is one simple example of a free oscillation. Now, I'll give you another one. This one is an approximate free oscillation. It's your simple pendulum, something like this. Right, so if you let the pendulum swing, you'll go all the way to the other side and swing back. And then you know, here, this is the equilibrium position. Okay, so there are many examples of free oscillations. Yeah, I think we are done with learning objective A. Okay, then the next part is actually the more hardcore stuff really. Okay, so look at B. They want you to investigate the motion of an oscillator using experimental and graphical methods. The TLDR for this, right, is basically can you illustrate an xt, vt, and at graph? If you can, then wow, it's quite easy, quite intuitive. Okay, so let me give you a simple example. So let's do learning objective B. Okay, so generally, if you have done a little practice on your oscillations, you always see, right, three graphs that come one after another. So typically, we start with displacement, and then from there, I can duplicate this to become velocity. And then I can duplicate this to become acceleration. Then honestly, quite easy one. You just need to first care about what kind of shape of graph you have. Okay, so you either have a sine graph or a cosine graph, and it's either a positive sine graph or a negative sine graph, or positive cosine graph or negative cosine graph. So then I always get this question, which is how do I know whether it is a positive or negative graph? And how do I know whether it's a sine graph or cosine graph? Now, for these kind of questions, well, you need to see the starting position, and then you also need to define which direction is positive. Okay, so in this example, oh, so convenient. I can drag my drawing here. Okay, let's say I have this. Okay, so this is my equilibrium position. Let me be meter. Okay, and let's say this is time zero. Okay, so at time zero, it's at the center. Okay, let's imagine that. And assume is already oscillating. So this is time zero. If this is already time zero, and then it's going this direction. Okay, so imagine basically this block, right? Here, yeah. This block here. Imagine this at time zero, right? At the very next instant, it's moving to the right. Then it comes back, moves to the left, comes back, moves to the right, comes back, etc. Right? Then you know that we can track its displacement. But more importantly, right, what we must first do is basically define a positive direction. Now, typically in exam questions, they give you the freedom to define whether it's positive or negative. However, sometimes they actually already indicate the direction. In that case, right, then you have to refer to the context of the question. Okay, but for my simple example here, let's take positive as rightwards. Okay, then see at time zero, if it is already at the equilibrium position, then the logic is, well, you must start here. The displacement is zero at time zero. Right? So x is displacement. At time zero, if it's at the equilibrium position, you end up with a very, very nice sine graph. Okay, so I think quite straightforward. Okay, but obviously I can show you the other case now. So what if we didn't start at that position at the original time? Okay, then let me erase this. Okay, so imagine we started here instead. At time zero, right, we were at the amplitude position. Let's draw something like this. Then I'll draw that this is time zero. Then how? Then you end up with a cosine graph. Okay? So I'll answer the very, very common question, which is this. Okay, how to tell if sine or cosine graph? Then the answer is at time zero, find the position. So if it is at equilibrium, at t equals to 0, then we have a sine graph. Quite intuitive, right? Conversely, if we are at the amplitude, then you have a cosine graph. Okay quite easy. Okay, so from there, all you need to do is just draw the graph like that. Okay, so a simple one. In this case, let's stick with our sine graph. Okay, so let's say at time zero, I'm at my equilibrium position. I end up with. Okay, and very important, guys. For this kind of thing, right, you must make sure you know the mathematical expression for this. Okay, so you know this is t. Okay, and you also know this is x naught. Okay, so quite easy. Thereafter, we can come up with an expression for this shape. So let's write it here. If I have a graph that I want to describe, I know that I'm looking at x, right? It's going to be it's a sine function, so I have sine here. And then the thing inside the bracket is omega t. Then the amplitude is x naught. So if you have this shape, you can say that the displacement is given by x naught sine omega t. Okay, easy. Now that you have this right, what the hell? Velocity and acceleration. Walk in the park. Okay. Why? Because v is just dx dt. And so you have the x naught sine omega t dt. Then you just differentiate lor. Then you get this. Oops. Okay. That's it. Okay, and yeah, so sometimes your school, right, will also write it this way. Then realize, right, I'm trying to prompt you that this thing is just the max velocity. So you can also write it as v naught cos omega t. Okay, so you can draw it out. So let me be neat about this. One sec. Okay, so right here at, so sure. Okay, wait let me just go all the way down. There we go. Same thing here. Okay, yeah. Then all I need to do is draw the graph. So I'll box it up for you. Yeah. Okay. Then notice v is just v naught cos omega t. Okay. So I just need to draw a cosine function. So I can plot it out. It looks something like this. Yeah. Okay. So yeah, once you're done with this, then wow, easy. You can finally get acceleration. And well, by intuition and all the way back from what kinematics, you already would know that acceleration is the rate of change of velocity. So then it's the v naught cos omega t dt. Okay, but this isn't what they usually write lah. So they usually write the other method, which is omega x naught cos omega t dt. Okay, and so finally differentiate this long. You pull out the constants first, so you get omega x naught. Then you got the cosine omega t dt. Okay, so same idea. You want to differentiate cosine, so you get negative sine omega t. Then remember, right? You must also differentiate the inside. So after you differentiate the cosine omega t, you must differentiate omega t itself. So then I must times omega. So I end up with this one, minus omega square x naught sine omega t. This is A. Okay, so easy. You get a negative sine graph. So you can plot out what it looks like. So it looks something like this. Yikes. Okay. And then this is negative, this is omega square x naught. This is minus omega square x naught. Okay, so you get this pattern, which is A is minus omega square x naught sine omega t. Okay, then look, this one you'll see, I think as one of the next few learning objectives. But I might as well get you to discover this now. Look at this. Suspicious, right, this fellow? How come? Because if you go up, it's here. Right? So notice, this is none other than A equals minus omega square x. Okay, easy. Okay, so yeah, this is the three graphs that you must be very familiar with. Okay, so I have a very important tip for you. Always check whether it's a sine or cosine graph by looking at time zero. Okay, then I will also answer the second common question now. All right, in black. How to tell if it is a positive or negative graph? When I say positive or negative, I mean like, is it a plus sine omega graph? Sorry, plus sine omega t graph or minus sine omega t? So what I mean is your initial displacement, right, could have been like that also. Right? Then the idea is just determine if the question has specified a positive direction, then simply follow that direction. Okay, but if they didn't, right, which is actually most of the questions, then you can set the direction yourself. Okay, but I recommend always state the direction. Be very clear to yourself and your question. What is the direction that you're concerned about? Okay, so like which direction are you going to set as positive lah, in other words? Okay, easy. So we are done with B. Okay, then for the next part, this one is really easy. So you know what? I'm just gonna copy paste it real quick. So here is the next learning objective. Okay, so for this particular learning objective, right, we just try to strike off our amplitude, period, frequency, angular frequency, phase difference, and yeah, okay, let's do that first. So what the hell is amplitude? Okay, amplitude, right, is x naught, and we define it this way: is the maximum displacement from the equilibrium position. That's it. Okay, so graphically, right, it's this fellow law. This is x naught. Okay, sick. So yeah, let me just pick this. Okay, then what the hell is period? T. This is just the time taken for one oscillation. Okay, and then done. Next, we also have frequency. Oh, should just write it. Okay, wait. It's always small f, not big f. Okay, and then from here, frequency is time taken. Oh, sorry, the number of complete oscillation per unit time. Then remember this, the SI unit is hertz. Yeah, I might as well write this also. Okay, wait. And SI unit for period is seconds. And then for displacement, it was for amplitude, sorry, SI unit is meter. Okay, so these two are related. You should know this from Sec 4 physics. Frequency is just 1 over the period. Okay, so okay, amazing. Now we end up with this one, angular frequency. Okay, angular frequency, right? Low key quite interesting one. Like it's not a super simple concept, and a lot of people, right, mix it up with angular velocity. Now, the reason why they mix it up, right, is because it's the same symbol. But you must know, they are like very different concepts in H2 physics. Okay, so let's analyze angular frequency here. Okay, let me write the symbol first. Omega is angular frequency. Okay, now if you think I write an ugly W, right, it is how it looks like. Yeah, this is what omega looks like. Just a cursive W. Okay, so I'll write omega as angular frequency. Okay, and angular frequency is the rate of change of the phase angle. Okay, now remember, it is not the rate of change of angular displacement. That one was the circular motion version. Okay, so this one here is the oscillation version. Angular frequency is for oscillation. Angular velocity is for circular motion. They're not the same thing. You have to remember. So a couple of TYS questions actually tried to test this. Okay, so later I'll show you the difference between them. Okay, come. The angular frequency is the rate of change of the phase angle. So the phase angle, right, is this. It's phi. Okay, and so we can define phi this way. Okay, wait. Let me just put it nicely. Okay, so this is phi. Phi here refers to the stage of the oscillation. Okay? So that's what phase angle is. So for example, one full cycle, right, is going to be defined as 2 pi radians or 360 degrees. So then the phase is like the measure of where we are in the oscillation. So if let's say I have like the vibrating object like that, right? Like just now, imagine this is the equilibrium, like that. This is the equilibrium position. It vibrates left and right. So it's the same example as just now. Just imagine there's the spring here. Sorry, like this. Right? And then it basically slides right and left and etc. So let's say, right, this is the equilibrium. Then what I'm trying to say is, let me draw in red. This fella here goes to the right, back, left, back. Right? So the phase angle is measuring, exactly where in this cycle are we going to be at? Okay? So here's a simple example. Well, if you just started the oscillation, then your phase angle now at time 0 is 0 lah. Okay. On the flip side, if let's say right, you're moving all the way here and back, now that's going to be half a cycle. So the phase angle will be pi. Okay. Yeah. So quite intuitive. Okay. Then if you go the full cycle back here, then the phase angle will be 2 pi. Okay. So that's what phase angle is about. Okay. So let me remove this. Now then we can do it this way. This fellow omega is just d phi dt. Okay, which is also delta phi delta t. This here is the difference in the phase angle. So we can consider it this way lah. In one full period, I go through the entire phase of 2 pi. Yeah, so this is the formula. Okay, and then no surprise, I think you guys know already. You can factorize out the 1 over t. Then you get 2 pi f. So this is another formula. Okay, let me be neat now. Okay, one sec. That's it. Okay, quite intuitive. So yeah, what else do I have to cover? Okay, done with this. Phase difference we've covered already. That one's also actually, let me define it this way then. So phase difference is this delta phi. Okay, so this one they test quite a lot. So let me write it neatly. Okay. So delta phi here refers to phase difference. Okay, and phase difference is actually talking about the difference in the stages of oscillation, okay, between either two different waves or the same particle of the same wave slash oscillation at different points in time. So that's what phase difference is about lah. Okay, then I'll give you an example lah. Okay, so imagine let's say I'm running on a track here. Okay, so this is imagine a national stadium lah. Okay, then this is me, this event, and then let's say I'm running a race with Abi. Okay. So let's say we happen to run at the same frequency, same angular frequency, right? So I run this way and Abi runs this way. Now I've drawn it such that Abi is always like half of the entire cycle ahead of me, right? Well, honestly, he could also be half a cycle behind me. We wouldn't be able to tell unless we see who started first, right? So then what is the phase difference? Between us, we could say half a cycle has already passed. So then the phase difference between us, right, is just going to be pi. Now why pi? Because one full cycle is 2 pi. So then the phase difference between me and Abi would be pi only. Then you can write it as radians, or a valid presentation is also 180 degrees. And so that's the difference in phase. Okay. Now in exam, they might also give you concepts based on drawing. For example, like this. They draw one wave for you, like this. Let's call this x. T. Let's call this wave 1. Then they could very well get you to see phase 2. So let me draw in red. Sorry, in black. Something like this. Okay, let's call this 2. Then how do you find the phase difference? Not easy. So there are two ways to do it. So delta phi, you can measure in terms of this delta t. Okay, the fraction of a period that 1 and 2 are differing by. Okay, so it could be something like a delta t over the full period times 2 pi. So this is the first formula you have for phase difference. Okay, so that is when they give you period here. Okay, now you could also actually have a different kind of graph which goes this way. Like, okay. Something like this. And then we call this x, and then this one is d. So imagine like you take a picture, right, of a skipping rope. Okay, so imagine let's say this is me here, and then I play skipping rope very sadly with the wall. something like that, right? So imagine I just take a picture of my skipping rope compared to the wall, right? So all the way through. I just take a snapshot in time, okay? So it will look something like this. This is the displacement, followed by the distance from me. Okay, so this is me, and this is the distance that I'm measuring, somewhere through, right? So let's say I take 2 points. Suppose I take this point and this point. Then I want to compare, right? Their difference in phase. The ones at the very, very top, the other ones at the bottom, right? So on the graph, right, it will look something like this. I'm trying to find the phase difference of two different points on the same wave. So I'm trying to find this versus this. 1 versus 2. Then easy. Let me just get rid of this. The phase difference will just be like that. You find this difference in the distance. Okay, so write delta D over the whole wavelength, lambda, a times 2 pi. Okay, so this is also how you can get phase difference. Okay, so yeah, this is a very important concept. You'll see a lot in waves also. Okay, so you need to be comfortable with these two. Okay, so done with this. Okay, and so they want you to express period in terms of both frequency and angular frequency. So done, right? Because see, period is here, and you have the relationship with f already. So in other words, period is also 1 over f. At the same time, you also know that you can get it from here. T is 2 pi over omega. Okay, so done with this two things. Done. Okay, let me make it a bit neater. I'll send you all this file also, so it'll be a bit easier to follow. Okay, so let me write here. Okay. So yeah, done with C. Nice. Okay, then yeah, the next one is quite straightforward. They want you to recall and use the equation A is minus omega squared x as the defining equation of SHM. Okay, this one, right, is a very, very straightforward concept, but you must know how A level test it. Okay, so let me make a new page. Okay. So you must first remember that this is the defining equation of SHM. Then they love to test you, right, what are the conditions for an oscillation to be a simple harmonic motion. Then there are two, and they're very, very strict. Okay, so the first condition is this. The acceleration must be directly proportional to the displacement. Okay, second condition is this. The direction of acceleration must be opposite to the direction of displacement. Okay, so there are two rules for this. And actually the first one is just saying this, right? A is proportional to x. The second one is A is basically opposite in direction from x. Now, very nicely, right, I always combine this into one condition. So let me just erase this and I'll show you the combined one. It goes this way. A is proportional to minus x. Okay, now look, there's another way to write the condition number 2. Okay, and the second way to write condition number 2 is the direction of acceleration is always towards the center. In other words, the equilibrium. Okay, and this one, right, it's actually a very important finding. So let me show you what I mean. So suppose this is a flat bench, and then this is the same mesh spring system. Okay, so this is a spring. Okay. Now notice, right, that the condition number 2 says that the acceleration is always opposite to displacement, right? So meaning if, let's say I displace the fella this way, so this is x, I know that the acceleration, right, once I drag it to the right, must be this way. Then I hope you can visualize, right? Oh, that means if I were to drag this particular box From here, I drag it to the right. Then the displacement is this way. The acceleration is always towards the original position, the equilibrium position. Okay? So if A and X are in opposite directions, you will always get the object going back to the center, to the equilibrium position. Okay, so this one super crucial that you must remember. Okay, so how do they test this in exam? Oh, they expect you to know how to draw the graph lah. Okay, then low key quite easy one. Okay, look, A, X, right? So we want to have direct proportion. So we know we need a straight line graph, but they are opposite in direction. So therefore, you get this exact graph. Okay, so look, important features to prove that it is SHM. First one, so acceleration is directly proportional, right? Okay, so this one right means it must be a straight line graph. Second, it must cut origin. So a lot of people forget this. Must remember, it must cut origin. And finally, you also must have negative gradient. So you get a negative gradient graph. Okay, negative straight line graph cutting through the origin. Okay, so yeah, if you see this in the exam, then you can say, okay, pass. This is considered simple harmonic motion. Okay, so yeah, done with objective D. Okay, let me just quickly share about one more thing. So look, not all oscillations, right, will be simple harmonic one. So for example, right, in the TYS, if you run through the oscillations topical, you'll see, right, they actually tested one graph, right, where this is A, this is X. Then they have just this weird shape, something like that lah. Okay, so it can be any nonsense shape. Just take note, acceleration is always opposite to displacement based on my graph here, right? This already means, right, that visually, you try to imagine a picture like this. So when I drag the object to the right, then it will try to accelerate back to the rest position, the equilibrium position. So this graph, right, guarantees, right, that there will be an oscillation already. You'll always go back to the equilibrium position. So this means there will be an oscillation. And in my head, I'm thinking that since acceleration is always directed to the center, right? So notice that if A is negatively related to X at all points, right? Or it's guaranteed you will have an oscillation. Okay, but is this SHM? Then the answer is no, because there is no direct proportion here. And so this kind of oscillation is not a simple harmonic one, but it's still an oscillation nonetheless. Okay, yeah, so let's get that out of the way. Done with this. Okay, then look at the next one. What the hell we do already? Okay, so recognize and use X is X naught sine omega t as the solution to this equation. So they're just trying to tell you must know these equations, and you must know that you can sub this into here. So yeah, when you do the questions, right, basically be aware that you can use this and this. Okay, so I'll mark off P. Okay, then the next one, you must also recognize these two equations. Okay, just now we proved out already, right? V is V naught cosine omega t, and I haven't proven this. Okay, so we'll mark out F, but take note, you don't need to know the proof. Yeah, so for that reason, I don't really want to bog you down with this. This video is going to be quite long already. Just take note, you can use this equation. Okay, so velocity of the particle in SHM, you can get it in terms of the displacement. Okay, where do you find this equation? You'll find it in the formula sheet lah. Yeah, let's do that real quick. Okay, so where is it? There. Okay, so this is the velocity of a particle in SHM. Okay, and you get this plus minus omega x naught square minus x square. Yeah. Okay, so it should be quite easy. Yeah, then we're done with DEF already. Yeah, we're also done with this. Describe with graphical illustration, change in displacement, velocity, and acceleration. So in other words, it was the same oscillations graph that we were drawing lah. Okay, so I combined it with this just now. Okay, so done. And then yeah, this is the hard, annoying one. Okay, I will not say it's hard. I'll just say it's tedious and a lot of stuff that you must remember. Okay, so for H, right, I recommend you derive from scratch. Okay, and you will take, I think, about 2 pages lah. Okay, so let's do the following. Energy in oscillation. Okay, but there are two versions of it. So let's just write the following. This one is with respect to time. Okay, if it's with respect to time, right, all you need to do is start off with a xt graph. Okay, so let's do that. Okay, and then I'm going to show you the vt graph. And then we don't care about acceleration in this case. Trust. You only need x, t, v, t. And then always remember, right, you need to care about where you're starting. Okay, so what I mean is, let's just say we have the same setup, right? So something like this. Okay. Then you have the object, the mass that's displaced. Okay, so the mass is displaced either left or right. Now here's the most important thing. Does it start at the center or does it start at the amplitude? So you consider at time 0, where are we? Okay, just now I already do the easy one. I already said, okay, we start at the center, the equilibrium at time 0. So you know what? I'm just going to make it a bit harder. Let's say, right, when it was time 0, it was already here. So I'll copy this mass over and I'll drag it here. Let's say this is time 0, and x is x0. Then this here, on the other hand, this is my equilibrium position. Okay, so if I started, right, with the maximum displacement at time 0, then I hope you agree, my graph here, xt graph, is a cosine graph. Now, could it be positive cosine like that or negative cosine? So the answer is it could be either lah. Okay, so let's just be normal people. What I mean by that is take right as positive. Okay, that's what I mean by the normal thing. That's what we always do. Okay, but in some questions, right, you might need to investigate further about whether the right direction is always positive or it is positive, right? So you have to investigate and see whether the question tells you that. For now, because I get to set what I want, I'll say that, okay, let's just take right as positive. Okay, so what graph am I expecting? If at time 0, right, I'm already at the amplitude, then this is x0. Okay, and all you do, right, is you draw this. Okay, so this is the original equation. Let's do x is x0 cos omega t. How do we get velocity? Okay lah, easy. So v is vx dt, dx0 cos omega t dt. And then differentiate this, you should get omega x0 minus sine omega t. Okay, so you'll get something like this one. Okay, you can slowly verify this is a negative sine graph. This is t. This is omega x0 minus omega x0. Okay, so I started out with this because I need you to remember, if you want to consider energy, the easiest energy to get is simply the kinetic energy. Start with that. Hunt down the kinetic energy first. Then the rest is easy. Okay, so then straightforward, right? So I want you to think of it this way. There are 3 types of energies in an oscillation. So first one, Ke. Second one, okay, I know you're probably thinking, oh, straight away, right, I can immediately say potential energy. And I agree with you, but usually I want to work out total energy first. Okay, and I'll show you the intuition why in a short while. Finally, we have one last form of energy, which is potential energy. Okay, so let me start out first by saying Ke is the easiest to find. Then think of it is just half mv squared. Okay, and look, v is already here. So all you need to do, right, is just sub it in. So you get this, half m minus omega x naught sine omega t square. Now when you square this, right, you realize the minus will disappear. And then you get something really elegant. Let me be a bit neater. Okay. And this becomes this, half m omega square x naught square sine square omega t. Okay, so yeah, let's draw this sketch first lah. Easy. Oh, sorry, energy is always positive, so you don't need negative values. So just like that. So let's write energy measured in joules with respect to time. Okay, then actually quite straightforward. You'll get this KE graph. Okay, so it's a sine square graph. Now, I think I nagged at you all enough already. By now, I hope you remember, right? Sine square graph is the no McDonald graph, meaning you cannot draw a steep part at the end. So I'll show you what I mean. Let's just consider a sine square graph. Now, the way I learned it when I was in JC was this. This is a sine graph, right? Okay, so if you want to draw a sine square graph, you will just basically make this part positive, right? So in your head, right, you might be thinking this. It will be like that, right? But no, it won't be this, because this is a McDonald graph. So what do I mean by that? You see this part is sharp, right? So if you draw like this, right, you'll get penalized. Okay, so don't do that. So if you go and plot out on your GC, you can confirm with me that your sine square graph, right, will be very, very smooth. It will look something like this. Okay, and in particular, this is what you're gunning for. Okay, smooth, smooth, smooth. Okay, so yeah, we know how sine square graph looks like already. So we can just sketch that real quick here. So let's call this half a period, right? Because this is t, this is half t. And see, sine square graph, right? One period, right, is 2 full peaks. So like this. Okay. Okay, wow. Let me clone this. Okay, so, okay, so this is how it looks. And we'll call this KE. Okay, so kinetic energy with respect to time. Okay, done. Then, what is this value here? Now, I hope you agree, right? Well, it's a sine square graph. This here, the maximum value is 1. Right? So if I want to find the maximum KE, I should just be looking at the amplitude of this graph. So this is the max energy. Okay? So I'll write this here. This is half m omega square x naught square. Okay? And I'll draw a dotted line like this. Okay? Then I purposely do that, right? And I want to show you that, dude, it's damn easy. It's just TE. Because look, the maximum energy you get is also the total energy. So we write it straight away, right? Total energy is just the max KE. Okay, and then the idea as well is just this amplitude value. Okay, but let's say you didn't know this, right? And you didn't think of it this way. Is there any other way we can solve it? Then the answer is yes. It's just half m v naught square. V naught is the max velocity, which is none other than omega x naught square. So you end up with the same thing, half m omega square x naught square. Okay, and then I'll draw a straight line like that. Let me draw in red. Okay, this is total energy. Nice. Okay, then finally, I hope you can see why I chose to do potential energy lah. Okay, so potential energy, right, you cannot like self-derive one. Meaning you must always get potential energy, right, as just the difference between total and KE. And in my head, the way I'm thinking about this is total energy is made up of kinetic and potential. So if I want to get potential, I just take the total minus kinetic. Okay, then quite easy. From there, all you get is this half m omega square x naught square minus half m omega square x naught square sine square omega t. Okay, so wait, let me just get rid of this now. Okay, then there's some math to be done here. Okay, I hope y'all can see already. All you need to do, right, is factorize this fella. So yeah, I'll do that now. We get this. Okay. Now notice, we actually know this 1 minus sine square omega t thing. In math, I hope you agree that sine square x plus cosine square x is 1. Right? So if I go and bring the sine over, right, I get this. Right? And then check it out. Looks familiar, right? So we know that, okay, if I get 1 minus sine square omega t is none other than cosine square omega t. Okay, so that's how you can do this substitution. You get this. Okay, very nice. Finally, let's draw in, yeah, maybe I'll draw in black, yeah. So we'll draw a cosine square graph. Okay, so it will look something like this. Okay. Okay, and once again, just check no McDonald allowed, right? So it must be smooth at the end. Yeah, and this is basically kinetic energy, GPE, sorry, not GPE, just potential energy and total energy. Okay, yeah. So now you might also just have wondered, well, what kind of potential energies do we have? So the answer is, well, it depends. It could be a mix of potential in terms of gravitational potential and elastic potential, or any other form of stored energy. Okay, so that's why in oscillations, right, we don't care about the specific type of potential energy. But the most common one you'll see, right, is a mix of EPE and GPE. Okay, so yeah, that is, oh, we're not even done yet. Okay, this is just energy with respect to time. Okay, then the rest actually low-key brain dead. You just need to know where to start. Okay, so the second version is energy with respect to displacement. Okay, and this graph is very different from the other one. We'll draw this. Okay, so let's draw energy and then displacement. Okay, so I will show you the formulas first. Actually, you know what? No, let me show you the intuition first. Okay, I think the intuition will help you a lot. So consider a block like that. Then it's, yeah, like the same exact setup, right? We've done this multiple times already. Okay, so imagine this fella, right, is just vibrating left, right, left, right, left, right, because of a spring, right? Now imagine now we are now, let's say this is the equilibrium. Now once you've reached the amplitudal position, so something like you drag all the way to the right here. Let's say this is x naught. Now what is the Ke here? And I hope you agree, it has to be 0. Okay, at the amplitude position, right, the Ke die must be 0. Why? Because then you stop, then you turn, right? So for you to even reach this next position, you must stop there, right? If not, you keep going further, right? So if this is your maximum amplitude, then Ke there, velocity there will also be 0. Then your U-turn. Okay, so then we know when I have my maximum displacement x naught and minus x naught, my Ke, right, must die be 0. Okay, and then look, intuitively, you know that this means at the center, I must have the maximum energy. And so we can call this Ke max. Okay, easy. Now the only thing is, what is the shape? Okay, and I hope you can visualize. It's just you can probably guess this, but I'll prove it to you later. It's going to be a very nice parabola. And so this is the Ke max. Okay, now let's do the hardcore proof. Okay, quite easy. Trust. So Ke is half mp squared. Okay, then remember, right, we could actually sub this formula. D is plus minus omega x naught square minus x square. This one don't need to memorize, but you have to know it's in the formula list. So let me just annotate where you can find it. There. Okay, so in exams, just pluck it out from here. Okay, so good news. You sub this in, right, and you get a nice expression. Half m omega x naught square minus x square square. When you square this, the square root disappears. So you end up with this. Okay, and then I hope you agree with this also. Then do you agree with this? This is the KE max. Okay? So yeah, the reason I write it this way is because I want you to visualize, right, that you get this kind of shape. You see you get a minus x square graph, which is this one, right? It's a minus x square graph. Okay. And then you have some starting value. This is, you can think of it as your y-intercept. Then this is your, yeah, so this is your y-intercept. This is your value here. Okay, yeah, so that's the intuition behind the KE. Okay, then if your intuition is strong, you'd also immediately know, oh, we already got total energy, right? So I'm going to dot the line up here. The total energy is just the maximum kinetic energy, right? So all you need to do is sketch. Easy. Okay, yeah, we'll call this TE. Okay, yeah, and then let's just write this here. TE is KE max, which is just half m v naught square, half m omega x naught square. So half m omega square x naught square. Okay, so last thing, we also need to find an expression for potential energy. That one, once again, if your physics is like strong, your intuition is strong, you immediately know, okay, potential energy must just be the opposite of this graph, so that they add up to the total energy. So you should just look at this. Like, okay, okay, there we go. Okay, yeah, you can draw a bit nicer, but this is how it looks like. Okay, so this is PE. Now, if you want the formal equation for this, yeah, we can easily get it. So I hope you agree by PCE, principle of conservation of energy. Then potential energy is just total minus KE. Then the good news is we got total now, right? So it's just half m omega square x square, sorry, x naught square minus this thing, right? Because this is KE. Okay, so minus half m omega x naught square minus half m omega square x square. Okay, you expand this out, right? You'll get this. That is PE. Okay. So yeah, we have PE, KE, and TE. Okay, and you can verify the shape lah. So look, potential energy will have an x square graph shape. Very nice. What's this? In purple. Yeah. Okay, yeah. Yeah, this is it for energies actually. So I think it's quite intuitive. Okay, done. Okay. So yeah, actually this is all, by the way, right, if you're following with the notes and you want to read through it a little deeper, this last objective we've covered, right, is actually OSCE2. This whole part. Okay? So yeah, if you're referring to the Google Notes and you want to split it up, it stops at G. Okay? Okay, then next. So they also want you to know damped oscillation. Okay, and they also want you to know the effects of the degree of damping and the very important aspects of critical damping. Okay, so let's visualize this. Okay, oscillations, damping quite easy one. Okay, so damping is a process where the energy of an oscillation decays exponentially. In other words, basically decrease at a decreasing rate due to the presence of resistive force. Okay, so to help you visualize this, well, think of any system in real life. Okay, so for example, let's say a swinging pendulum. Now, if you let go of this pendulum in real life, it would eventually reach this vertical final position after it loses all its energy, right? So how come it loses energy? Because there is the presence of a damping force. And of course, it depends on the system, right? So in this particular case, the oscillation, right, is undergoing damping due to the presence of air resistance. Okay, so air resistance is the damping force. Okay, so yeah, this will basically erode the energy. Erode meaning the energy of the oscillations are gradually decreased over time. Okay, and so this also means the amplitude, right, decreases over time. Okay, so this is what damping is all about. How do you visualize this? Okay, but honestly, my drawing here is a bit hard lah. It's not very neat and nice. Okay, so don't worry, they won't ask you to sketch this to a high degree of accuracy. But you must remember this. You need to be able to show, right, that the amplitude will decay exponentially over time. Now, I mean, now that you're in J2, okay, I think you already know that, well, we've done this in nuclear also, right? The amplitude, right, will slowly drop. And when I say slowly drop, I mean it will decrease at a decreasing rate. Okay. So look, I will first draw what you're expected to remember, which is this. The amplitude, right, will decay over time. Like that. Will decrease at a decreasing rate. Okay, but in real life, remember, right, the thing is still going through an oscillation. So let's say this is the starting. Then we'll go through this. Like that. Yeah. So slowly decay over time. Okay, and so same thing here. Like, yeah. This is what damping looks like. Okay. Yeah. So okay, quite intuitive. Um, let me see. Have I missed out anything? Okay, no, yeah. So this is a practical example of a damped oscillator. Okay, yeah, okay. So then there are a few different types of dampings. Okay, so this is the general idea of damping. Then I need to show you the three forms of damping. Let's do it here. Okay, so die must remember this. This is light damping. Then we have heavy damping. Then we have critical damping. Okay, so for light damping, right, it's basically what we have just drawn just now. So the logic is this. The damping, or rather the amplitude, decreases at a decreasing rate. And more importantly, the oscillation still continues, but slowly dies down. So in particular, right, it will continue swinging for quite an extended period of time. So the amplitude gradually decays. Okay, so let me drag down this graph real quick. There we go. Okay. Yeah, this is how it looks like. How about heavy damping? Wow. Heavy damping, right? The best example I have for you is a door stopper. So I try to help you visualize this. Okay. Okay, let me write at the hinge. Yeah, it's this kind, right? So can visualize it? Okay, let me screenshot this. Okay. So yeah, think of it this way. It's a door stopper. So if you don't have this door stopper, right? The idea is the door, if you let's imagine now this is the side view of the door. Right? This is the hinge. And the hinge. Then the door is here. Right? It'll basically swing back and swing forward like a lot through the middle, right? And this is not what you want, Yeah. So this is usually heavily damped. So they put this system, which is this thing, at the top here. And this heavy damping, right, prevents the door from ever crossing the center point. So it's called heavy damping. Okay, then let me show you how this looks like on the graph. Heavy damping does this. This is x, and then this is t. So let's say your normal period is here t. Okay, this fella, right, will not even go to that. Let's say this is the usual period. If I just let it swing freely, right? It won't even like finish and reach at this point in time. It will take a very long time to go back to the origin. And more importantly, it doesn't ever go past x equals to 0. So it will never swing past. And you can visualize this on your door stopper. When you have this door stopper, right, you never swing forward past the gap. Right? So yeah, that's how heavy damping works. Okay. Wait out. Let me just neaten this up. Okay. And so I can write this here. So the amplitude decreases slowly. And the oscillation, or rather the oscillating body, never crosses the equilibrium position. Okay? So the oscillation dies down over time, and it takes a really long time to finish. Okay. So finally, you got critical damping. Now this one is the hardcore one, and it's the really useful one in real life. So let's draw something like this. This one here is x t again. And so imagine, right, there's a normal oscillation and it starts off at the amplitude x naught. Now, the critical damping, right, is this. You go down to the equilibrium position in the shortest possible time, and you never go past. So you just go straight like that. Then I'll draw it in black. You just go straight. Okay. And so this is it. The amplitude decreases to 0 in the shortest possible time. And the oscillation does not continue thereafter. Okay, so this is the fastest way to stop any object from oscillating. Okay, then down here you must remember, right, in what case do you want this? So, well, your syllabus expects you to know that a car suspension system is where you use it. So you basically ensure that, oh, if you go past a hump, then your car, right, isn't going to oscillate up and down, up and down. It's not going to do that. It's just immediately going to stop and be still. Okay, so that is how the oscillation system works. Okay, that's how the critical damping system works. Okay, so yeah, we've contrasted light damping, heavy damping, and critical damping. So you must be able to provide examples for each. So let me also just add one example for light damping. Okay, then the answer here is any particular oscillation in real life that eventually dies down. So example, something like your pendulum. Okay, so if there's some kind of air resistance on it, it will undergo light damping. Okay, yeah, that is pretty much this learning objective done. Okay, so next one. Oh, this one crucial. So we also then learn about this thing called a forced oscillation. Okay, then quite important. You look here. Forced oscillation, right, is not the same as free oscillation. They are very different. A forced oscillation is one whereby I also have some kind of periodic driving force. Okay, so I'll try to give you a simple example. Let's write this. Okay, so to make it easy for you to visualize, I'll draw the same setup as just now, right? And this is called a forced oscillation. Okay, so let's do something like this. We have the spring like that, and then notice instead of just letting it, like I drag it to the right like that, and then it just goes back and forth, right? Instead of just doing that, right, I must set up some other kind of periodic driving force. If I were to just let this swing, like left, right, then that's what we call a free oscillation. But I now want to analyze a forced oscillation. So I must draw some other system, something like this. Let me draw this. We'll call this a mechanical vibration system. Okay? So this mechanical vibration system, right, basically also pulls the mass back and forth, back and forth. So this here is called the, this particular force, this one, it's called the F driving. Then this force is the natural restoring force. Okay, so take note, for a force oscillation, it is defined as an oscillation whereby a periodic driving force acts on the system. Okay, then you must remember, right, whenever this occurs, the oscillation has, okay, will vibrate at the driving frequency. Okay, so that means, let's imagine the F driving, right? I supply at like 10 hertz. Okay, then the oscillation, right, will undergo this exact 10 hertz of oscillation, like 10 hertz frequency. So a force oscillation, right, the dominant force is the driving force, the driving, the external driving force, right? So it will vibrate at this 10 hertz. Okay, so yeah, must remember this. Okay, then wait, I should contrast it here. So go all the way back to the very best start. How about free oscillations then? Free oscillations, what do they undergo? What kind of frequency do they undergo? And this one, right, we should annotate. Okay lah. Actually, you know what? Let me just draw it here for you all here then. Okay, so how about if I had a free oscillation? So I'll draw this exact setup again. But this time around, I won't have this mechanical vibrational system. Then let's just call this a free oscillation. Yeah, so for free oscillations, what's the idea for this? What is the frequency going to be? Okay, and this is a very important question to ask yourself. It's actually not hard to prove. So let me show you the logic. Okay, so if you want to derive the frequency, right, it's actually simple. You just consider this. The F restoring provides for by the F spring. Okay, that was a little convoluted. I could actually write it this way also. F spring provides for F restoring. So it's familiar to you. In circular motion, you always did this also, right? So same idea here. Okay, so F spring provides for F restoring. So we can do it like this. F spring equals to F restoring. And then Kx equals to, okay, by the way, if you want to care about the negative sign, you can. So I'll do that here because remember that for Hooke's law, it tells you that the tension, right, is always opposite direction from the displacement. So there's also a minus here. Okay, and then now here, F restoring is ma. Okay, and remember, right, acceleration in SHM is going to be this. Okay, very nice, very nice. Okay, so in this case, we can cross out X. And then you get this. You can also cross out the minus, by the way. So you get K equals to M omega square. So you get this. Nice. And then I hope you agree, right? We already learned this now. 2 pi F is K over M. Right? K over M then square root. Okay, so if you want to get F, you get this. Okay. Okay, listen, don't memorize. Right? Be able to derive it yourself through this. Okay, so they sometimes ask for this. Okay. Now, what the hell is this frequency called? This one, die must know. This frequency, right, when you let it freely oscillate, is called the natural frequency. Okay, so yeah, I think the naming is quite intuitive. If you let anything oscillate freely, the frequency that it will oscillate at is called the natural frequency. Okay, so that's the difference between a free oscillation and a forced oscillation. A free oscillation will oscillate at the natural frequency. Okay, but a forced oscillation obeys the driving frequency. Oh, fantastic. Okay, yeah. So this one is a very crucial idea that you must know. Okay, then look. With this, we can suggest what happens if I provide a driving force periodically at the natural frequency. Okay, I think you guys can remember this already. We have a very crazy outcome. If I keep supplying energy right at the right time, I keep supplying that force that I need at the right time, I will end up with resonance. Okay, now I want to make it even more intuitive, so I'll give you a simple example. So let's imagine this is me on a chair. Okay, sorry, not a chair, a swing. That's crazy. Okay, and then let's say this is Ian. Okay, so Ian pushes me on a swing. Wow, that's crazy. So take note. Then I'll swing left and right, left and right. Okay. So naturally, if he push me once, right, then okay, let's put him aside. Then I will swing back, forth, back, forth. Okay. So what happens, right? If he times the push exactly right when I am right smack here in this position, this center position, then I'll keep going higher up, higher up, higher up, right? Because he pushes me at the right time. Okay. And that is resonance. So we can think of it this way. If F driving is supplied at the right time, this is the intuition. So we won't write it so informally. So you don't need to copy this if you are following. Just pay attention. This is intuition behind resonance. So if F driving is supplied at the right time, then the energy of the system would increase. And that's exactly what we expect to see. Okay, so this is resonance. And when we say at the right time, I hope you agree, it means Ian, who's pushing me here, must match my natural frequency. Then I really gain a lot of energy, swing all the way up and back. Okay, so then there's this simple outcome law. So if F driving equals F natural, then resonance will occur. And what do I even mean by this? Simple. This means the object will have maximal amplitude. Okay, so why? Because amplitude is proportional to the energy. Okay, the amplitude square is proportional to the energy. Okay, so I'll justify myself, but let me draw out the graph for you first. You die must remember this graph. So we'll call this amplitude. And then we'll call this frequency. Then you die just need to remember at the natural frequency. We'll call this F naught. You end up with this. Right. Okay lah. Wait, I'll be neater about this. Okay, there we go. Nice. Okay. So this is resonance. Okay. Okay, then actually your syllabus expect you to know one more thing. Okay. Okay, so let's draw this. What is the effect of damping on this graph? Okay. Now, okay, let's try to build the intuition for this. So why do we care about the effect of damping? Now think about it this way. So if there's some damping, right, like this, damping would slow down the oscillation, right? So it's like there's some resistive force, so you take a longer time to complete one cycle. And so do you agree that the true T will decrease? Sorry, not okay. I should write it as the effective T, and my bad is increase. Yeah. Okay. Why? Because you slow down, right? So your period is longer, right? So you will vibrate slower. So in the context of the swing, right? So in the context of the swing here, if there's like some super resistive winds, let's say there's air resistance, right? As I'm flying up, I'll take a longer time to fly up and then slowly come back down, so, right? Because there's a lot of damping forces against me. Then in that case, my one full swing is going to take a longer time, right? Okay, so that's how this you can think of it. So what does that mean? That means Ian, right, should push me at a slower rate also, because he wants to match my effective period, right? So yeah, if there's damping, then I hope you agree with me that his frequency that he pushes me at should decrease so that I get the maximum energy transfer. He must push me a bit slower. So then the graph will look like this. Call this F prime. And this graph, it shows the effect of damping. Okay, so look, main idea is the amplitude will not be as high as before, except for when frequency is zero. Okay, so why? Because if the frequency is zero, right, that means you're not even pushing anything, right? That's why this point is still the same. But all other frequencies is lower, right? So the amplitude is lower. And then the maxima occurs to the left. Okay, so we can think of it this way. Thus, damping shifts the resonant frequency. And I want you to remember the resonant frequency as frequency where max amplitude occurs. Leftwards. Okay, in other words, decreases frequency. Also, decreases amplitude. That's it. Okay, so let's go back up. So yeah, done with this. Okay. Describe graphically how the amplitude changes with driving frequency. And understand qualitatively the factors that determine frequency response and sharpness of the resonance. Yeah, we have just done this. Okay, so done. Okay, yeah, the last one is quite easy lah. So they finally test you some stupid stuff like when is resonance useful and when is resonance not useful. So for this one, I would honestly, I mean, if you can build the intuition to this, read the examples in the notes. Okay, so it should be in part 2. There you go. Let me find it for you real quick. Yeah, so this is useful cases and destructive cases. Yeah, I think yeah, I'll leave this to you as self-reading lah. Okay, so it's not much like say there's a bit of logic here, but you just need to remember when it's useful and when it's destructive. My recommendation is knowing when it's dangerous lah. Okay, so my own when I was in J2, the ones I remember was just earthquakes as well as the famous Tacoma Bridge. Yeah, I believe it's called the Tacoma Bridge. Let me check. Yeah, that's right. Cool. So the Tacoma Bridge actually undergone resonance. So it didn't actually crash at the wrong time lah. So the good news is I think it averted a lot of deaths because it was already swinging like crazy when people were walking. Okay, so there were a lot of people that were walking on this bridge, and then they walked in step. So when they walk in step, right, the external driving force based on their legs actually provided for the driving force that matched the natural frequency for the bridge. And then it caused the bridge to sway a lot, left and right, left and right. And the idea is, yeah, when this occurred, the officials thankfully prevented people from further causing a strain on the bridge. So actually prevented a lot of people from dying, right? And yeah, this eventually still collapsed due to the external winds and etc. Right, so this is dangerous resonance. Okay, so on the other hand, what is an example of a good resonance? Well, the easy one you can think of is musical instrument, right? So if you want to produce a particular sound tune, you can actually use an instrument and you send in a sound wave that matches the natural frequency. And actually, you've learned this in another chapter called superposition. Okay, but yeah, I don't want to dive too deep into this. If not, this video will get even longer. And you can also remember microwave cooking. Okay, so microwave cooking is easy. Basically, you send in microwaves which have a frequency near to the frequency of water, the natural frequency of water. So then the water molecules will oscillate at a much greater amplitude, and then they have higher energy, and so then they cook the food around them. Okay, so yeah, this is how microwave cooking. Okay, so I'll remember this and this. Okay, and then if you're studying superposition, of course, remember this. Then, yeah, we're almost done. Okay, last thing. So I believe I have one other weird graph to get you to remember. So recall, right, that you also have this graph. Okay, so sometimes they expect you to know that they give you this formula already, right? V and X. It should be omega X naught square minus X square. Yeah, then you just need to know, sometimes they give you this stupid graph, right? You also need to know the shape. So it looks like this. Right. Yeah. And so basically it's a it's this oval shape. It's a conic graph, right? And it's called ellipse, right? So you get elliptical graph. And this is this region, this line is gonna be v is plus omega x naught square minus x square. Then this other part here, in orange, is the negative version of. So quite easy lah. This is minus omega x naught square minus x square. Okay, so you must also know this works, and you can use this in exams. Okay, if not, yeah, congrats. You are done with the revision for oscillation. I would say that okay, you probably have enough grounds to like start practicing questions already. Okay, so watching this video alone is definitely not enough. Please go and start doing the oscillations learning objectives. So you can head over to the website, go to oscillations, and start the grind. Okay, so there are some questions where they aren't like tagged objectives because they're not so granular lah. So the questions don't test just that thing. Okay, then after that, go and do all the questions here. Now there are plenty more below for extra practice if you need. Okay, if not, yeah, that's all. See you guys on the extra class soon.